Basically, I've got my notes again. But this video is very important. If you don't understand the importance of this, I think you gotta be blind to the whole thing. So let me just put it like this. Don't get to be blind to this. This is geometric computing. So biological computing for sparse data. So that's a canonical term. So the canonical user for all the polygon systems. So you got Mmuko, M for Mike, M for Mike, U for umbrella, K for kilo, O for Oscar, dash C dash like a hyphen, C which stands for consensus ID. Now that's consensus ID. That's like a Mmuko ID systems with a tripartite DAG relationship and diamond dependency medication based on directed symbiotic evolution, which just means it's like the evolution is geared towards some objective to reach a resolution. But these repositories are really essential for the system. So let me start out. GitHub.com//O for Oscar, B for Bravo, I for Indigo, N for November, E for Echo, X for X-ray, U for Umbrella, S for Sarah, G for Gal, I for Indigo, T for Tango, hyphen, R for Romeo, A for Apple, and F for Fred. That's git dash raf. That's basically the governance behind this. But don't want to talk about that. Basically, it's like system can govern itself, can respect its own state. Basically, there's no governor. So this crew can first of all govern itself. Let me see if I can get this up. Because it's based on this, so I have to like try and at least trying to do it. Oh, this is my friends. I'm trying to find the right website to do it. Yes, this is it basically. 10. Scene. This one here. So that's Mmuko C time. But let's start with Git Raf. So I'm on a computer. This is good enough. This stands for regulation as firmware. So it's like a govern. So this is governance strategy. Who governs the governor? Who has the final say? What if two policies fight? So basically, no, I'm the governor. No. Basically, this is like a team. Who has authority? There's no authority whatsoever in the system. First of all, no one gets priority. Just do your job. So basically, RAF regulation by competence. You govern what you're meant to do. You do the best stuff. You do what you're good at. The best at it. No one ever should tell me about this. You do ABC. So this is governance. This is Oracle. It checks the entropy and it plays text. Basically, what it does is tracks your artifacts. It's git rough, but it's regulation as firmware. So you got the git sub-module document indexing. But this is git rough. And this is the first one. Problem 2: govern the governor. Who holds the power over the rule makers? So basically, there's no rule makers. Governance is governed. So all policy was about vector. Basically, if you make a wrong move, the sparse is something like a sparse artifact, but it has like a vector to it, and that vector is malicious. That's kind of vector. So basically, how this works in practice is like if you have like a some kind of a file that it's like a virus, but it's a zip file, but you get execution rights to that file. You can take it. You can basically go out the directory you're meant to be in code root, but that root is dot slash. But you get an artifact dot slash, and you load that artifact as a zip file from dot slash, which is your own system and the road, and you then execute that artifact like it's a zip file with zero file. So that is just like a Python script. But after can load itself, so it's like an elf system. So the system loads the virus because the system can code onto the virus if you escape the path. But you can't govern. So you got to govern everything. So that's the governor, governor province. So the governor can govern. But if you have like a malicious artifact, you shouldn't be able to load it up in the first place or get access to it. So that's the thing. With the path, so you get connectize all the systems to make sure that you have the root and you have isolation of concern from the what is permissions path row, and then that will allow you to load anything that has traversed the index that is served onto the system for the user interface or the terminal tier interface. Problem 1: I'm the governor. No, you're not. So, but who decides to go? No one decides to go. No one should govern what the only ones you need. This is Oracle. Now, the Oracle algorithm is like geometry tracker. It tracks the seal And if I give you an Oracle, you get Oracle 512, which tracks the state of two public keys and one private key. So the two public keys again are access codes to two public keys. But I can switch my role in that spot specifically. I can take two public keys and one private key, and then I can switch. I can make the one I'm active, the one private key I'm active on, the private key, and switch the roles. But it remain integrity because I have two public keys now. I share one state. Who is the power? No, no. It's given from T. Find out when particular class. Two varieties, one runtime part. Who wins? Rough telemetry based solution. So basically, this is sparse modeling. So, but sparse means you can model it anyhow. Two policies are valid. One runtime path. Who wins? This like an interpretation thing. Something is a misinterpretation or something commonly. Who's governor? So telemetry interest scores roll backwards. So governance is by reality check. So basically, you can govern. You can say you have a role, but the real world behavior is monitored. So you're gonna monitor everything until you prove you are the one that's meant to govern it. Because if you're good at then who's the best when you fight about it, you basically my version you have consensus, but this is you don't say here. So you get like a consensus model. So you do one, you try one, and the second time someone that tries something, you get something else. So this is like a firmware governance. So this is first trial between two people. Someone they get the same thing, get the best. With the best is the best, and then someone else then has to get it right the second time. If they both get it right the second time, they can both govern. Separate part of the artifact, or just one part if they and then but if they get a third trial, the consists of who's the best of the best. Three trials, one person at least can fail. If person they can the development team can grow, which is why a good thing. So Act 2 basically, this is just the problem. Who governs the governor? No Oracle tag entropy stability. So entropy stability, there's no like a the code code engine uniform canonical sure, Unicode canonical UCSN character set universal character set normalization. So that's just normal. Basically, that means the UC and Unicode character sets normalization. So basically, that is like Unicode is like the thing you use to code everything, but the canonical just means works across all systems, platforms, Windows, Linux, Linux. Linux is very good. And what's one I know? I don't remember that one. What do I remember? But it's Debian, Debian. So you get canonical just means it works across all systems. The normal one is the Unicode canonical character set. UCN and character set, the set of characters you're encoding, what is ASCII within Unicode, and the normalization just means the shortest path to do that. But that's what I'm saying. That is a view specification. Now, so this is like how it works in practice. So, Twitch, a new Rifter, Act 1. So, hey, so this is like very nice. I also do this. Hey, C1, everything just joined. Why is it fresh from chaos? Get commit, chore, in it. Welcome to the Rifters. Welcome to Rifters. Welcome you Rifter to breathe. Add policy tag. Import decks on for onboarding. Oh, so chore in it. Chore, your chore. This here we don't narrative. Here we don't fix hotfix. We don't code our panic. We come here with care. Every chair is every chair is so basically you code it for yourself. But the in this is like I code for myself. There's no chore I'm doing. I'm trying to start up onboarding. See how this git ref works. Every thread is accounted for. This is Polygon, by the way. Act 2, the conflict. The debate continues. The comment. Scene 2, two rifters collide in a firmware direction. So basically, the firmware is like the hardware. And you got a silicon, which is just a small block of code that's on the system. But it's like I don't even like that one. So that one's too rigid. One priority is hardware. The other demands aura compliance. Git commit dash m fits a feature conflict. Basically just like a feature, but in it, debate a policy directions path without oral seal. Who said this? Why does it matter if it's sealed? Well, have to use when we got a brick device. So basically, the brick device just means this just is the brick because it's very good to understand the conflict as the brick, and it's actually a reflection of the user intent, statement, expression. Basically, you're thinking about the user, not even you guys coding it. So when it gets brick, it's because the user done something. So you detect it as well. derivation rise, frustration grows, but you can make it. You can go that direction. Each hold the ground at 3 rotation. Hey, middle path. The milestone shipped with partials, because basically this 1, 2, 3 is problem addressing each problem. Two, each holds their ground. So basically, they bring the device, and they do know the governor don't get governed. They don't override. Just put this a conflict, and they uh basically that's regulation of firmware. Frustration grows. Each holds up to the right resolution. The aura field. This is like an aura field. Like it's this topology section. A middle part. The middle governance is perceived. The rate happen. Git commit dash m. Final compromise. Add entropy checksum. But basically this is kind of corporatization. Uh, the book What Away, not as winners, but as rifters. This is about the Rift project. Rift is a flexible translator because they are, guys, I'm a rifter. Because I'm a winner too, but they don't win. They work together, redefined. What's our purpose? What's our goals? Because Rift, this is because this is not Yak. That's the Rift tool. So what's we here to talk about? So here's to talk about this thing here on my paper. So what's the next thing I'm going to talk about here? Basically, I got a work example here, but I'm just going to directories for you guys, just so my alarm doesn't ring and I stop for 5 minutes. I can post to YouTube. YouTube, I get it done. So the next one is this. That's GitRef. And then we'll go. What? This is Mmuko C time. Now C time is just what I made today, but I don't. This is C time. I don't want to talk about C time yet. Now gating philosophy. This is like gating, but this is C time. Oh, sorry, I put the wrong rotation. It's like gating. Sorry, but C time is Mmuko dash C time. That stands for like constitutional time. So it's the wrong place basically. I mean, in consensus time, time you consent to, consensus bound systems. That's Mmuko OS. Sorry, Mmuko. I should be. That means there's nothing here. Yep. Yes, Mmuko. Basically, this is the system working on the operating system. But it's a platform. Basically, I'm trying to ship all this to a platform. So this is the architecture. So Mmuko Spirit, Kaju rhythm. So this is like a Mmuko metaphor. Metaphor. Basically, anything I don't like, I paralyze it. One systems fail will breathe first. We literally breathe first. But that's what I'm saying. So basically, I'm trying to find what's most related to this. That's it. Semantic versioning. Extend. So this is the same thing here. This is semantic version X, but we got the Mmuko OS, which is really GitRaf bound and semantic version X bound, but this should not work here. This is just like canonical. So that's the so this Rust, basically the same thing. The Rust one is just so what it is this. This is what we're talking about. This is very good now, but it's not complete. So this is the what I'm going to talk about now. So we got GitRaf, semantic version X and what NSC, which stands for Next Search Indexing. No, but NSC is Git SDK. Okay, let me start this on this. Okay, so you see this here, guys? I'm switching back and forth. Let me just find the paper I found first, because this is very hard for you to understand, guys, because it's new, and I want you guys to take it as new, and not leave me in the. If it is new, if it's partially new. So we got this. What am I trying to model now? I'm trying to draw a definition tree. So sparse, a sparse system. Something sparse has a two ways it represents itself. Two ways. So like a square, x is what sparse model. It has what a square. Square is 4 sides. And then x is square, but it's two ways, two operations you can do. And then other one is sparse too. So you can have a circle and a triangle, but that's sparse too. But they just they have edges. They just one has edges, one doesn't have edges. They're closed and it's sparse. They're closed loops and it's sparse. But you can have things that are not that sparse, but not like this one. So you get like a up, something like a U shape, going up on U shape. Now this is a spark model, but it's an up and down. It's like you get a two up and a down, or something pointing up like a trident. Where the trident goes up and down, something like that. Which is basically topology modeling, computationally, of course. Scene for 2 here. Here, guys. So this one's saying fake or real. Go like this. Fake sparse defense, Child King. This is a very good poem. I even love this. This is sparse modeling, so it's not the sparse gonna work with. Basically, you have to understand that these systems are very dynamic, biological systems. But I'm trying to literally use the video to simulate things like diamond dependency, and actually not simulate it, emulate it, and resolve it. Because I want to real-time emulator. Based on biology. But this model I have here, the biological model I have here, but I'll come back to that later because that's a fine example. So guys, I want you guys to take this video and you can solve your biology issues too. I don't really care how you use it. You don't have to contact me for license. It's on GitHub. It's gonna be on GitHub anyway. My GitHub page. But let's do it properly. So Namdi, so what have we done here? So I've got it's 2, 3. No, I need this 6, 7. No, I've already done this one. So I need this one. I need it done properly, Namdi. Sorry, I'm just no. So this is one. Okay, no, just it's gotta be here somewhere. No. I know where it is. No, I didn't put it there. Okay, this is sorry. This is what people say. See, I'm just very disorganized now. So basically, I'm looking for that paper. I can start it without it actually. Let me just start it without it. Oh yes, this is here. So see this. I'm gonna put my camera on now. This here. Oh no, this is not the one. See this here. No, this is the foundation of it. So it's very rigid now, but I'm going to use the computer on. So this is topology mesh, dynamic topology meshing for sparse modeling. Basically, the Mmuko OS, European Mmuko is in GitHub. You see the Mmuko, these are really biological systems, but sustained for biology before us. They're sustained for us because we are the foundation. So their foundation is sparse. So this is why it's very important for threat modeling. Now, threat modeling, why? It's basically genome. So you got problems like RSA, but as systems evolve like that, the biology is more stable. So basically, you're gonna some of the biology problems are just new because it's computers are doing it, but they have to have a consensus to do it before they do it, because consensus is very important for them to do it. If I say no to my gene, if I give instruction, if I write some instruction for to take to get cancer, I code once, I code twice, and I code 3 times. And basically, I'm saying like if the system, if the cancer genes if I keep smoking, the gene will naturally increase the rut, the growth rate of the rut of the because the thing will just naturally be prone to degradation because my body cannot take my lungs breathing and I'll get lung cancer. Because that's tissues in cancer cell. But I'm trying to solve a lot of other forms of cancer in it. But I'm not doing cancer because I'm trying to get right simulations and emulations, all the same thing like HTML simulations like based on sparse model for dynamic systems. So things like HIV are curable, but I'm basically doing biology and what I call sparse biology. I'm make it sparse biology for dynamic motion. So you got like a circle, which can mean like a codon, and got next like a circle next. But the homogeneous heterogeneous models that do the same thing or something else. So I'm gonna give you HIV/AIDS. Think of like as things. Think of it like viruses and bacteria, but for computers, running on computers. So we got RNA. So introduction, sparse biology. So the goal of this is to literally create things that new kind of antigen, a new kind of medicine that is not in my body all the time. Sorry. Anyway, so RNA stands for it's basically DNA. It's a DNA strand. So basically, you understand the terminology. RNA stands for it's a reader. It does things you can read, or and write at the same time in one sequence. Or series of a code. So read and write is an RNA. So you're gonna understand this properly. So let me give you the breakdown. So anybody's not familiar with biology can get it quickly. Because I have to remember my biology now too, unless I don't get it right. Oh guys. So basically, RNA is made of 2 things: a reader RNA sequence. Somebody can read your genetic code. RNA reader. Let's call it RNA reader. An RNA writer. Think of this as like Lexus in computer science. Lexus. But the work on a genes, not the standard tokens. This is the Gossilang.gs files are RNA bound because much of this is just structure, the structure of what you're modeling. But basically, it's like bidirectional structure of a syntax. So if I read in syntax, the ref R. So I'm just gonna give you the overview now. So I'm gonna go back to my tree. I'm gonna try to find the ref thing. 20 minutes. So basically, you can do two things here. So this is like so you this is like a schema: service, the operation, the department, the division, the country, the org. Because we live in classes, we have constitutions. But this constitution is rotation. So basically, this service is the right angle bracket for it. But it's a schema, so you can put a service here, like here, sales.demo.ob next to the silicon, the computer.uk.org.uk. So this one component, we can go to support ticket. So basically, it's going to find the service you need. We try like part-type consensus. You are given consensus to index where you just punch in this service and you find your. It's basically like instead of you type in numbers anymore, you just punch in a schema onto your web URL and you get what you need. Mmuko services. But you have to get consensus to it. Because if you say yes, computer once, you just say yes again and you say no, so you don't consent to it. But then if you say yes again, you get consensus. So it's 2-to-1 mapping, tri-directional mapping, that's a schema. But this can be nil, nil, nil. So let's go to the rift now. Rift. Rift. So you get rift. So this is like the rift docker, rift way. Rift in. Why do I okay, let me just put rift in because rift. So this is a rift. So this stands for rift is a flexible translator. This just means that it uses a pattern matching. So I want to give an update ratio. So this one, so you go like an R. So this how it works. So this how it works. So basically, you got my name, Mister, which is just my I need something my first. So I put my title, the title name, and that'll be like in a box, but in a circle because I'm not in a box. I don't want to be in a box. In a circle, and then I type in my title. I switch my title to Mister because I'm a man, or I can switch my title to Mister as in a child, MISTSR. This is for children as well. Because a child, no, sorry, that's a Mister, is a woman. I'm a master because I'm a man. I'm a child man. So identify. This is silly, man. I have to get rid of this. But I don't really care because I'm okay. Master, so I'm a child. But then we get Namdi, first name, middle name Michael, Namdi. So this is my N dot M. M, which is my initials. So just put an M. N Namdi Michael. So this is a schema I can format for every names. Because this is title, and then I put my title name. But in my title name, I have meditated. So my avatar name, or so-called my persona or avatar name. Come on, do it now with you guys. Persona, Mr. OBI, Nexus, Hearts Collections. This is like my nickname for my games or my videos or how I want to do my Phantom ID. Because it's about building authentic persona development. OpenSS Namdi Michael. So my name is now. So let's take my. Let me give you how this works. In the real world context. It's 30 minutes. Don't give a shit. So this is Rift. I'm gonna cover Rift now. So I'm just giving you an overview of the OpenSS setup. So now, AS2, AS squared, AS2. Oh, sorry. Oh, I didn't change this. Okay, basically this is just a AS2 plus splicing. So this AS2 splicing is the AS squared. This is like AS2. This is AS2. This is like A squared. This is a sequence space. So this sequence space is just a segment of property space to you. Property. But this I'm saying to you. This what's the works with. So basically, this is what it uses. It's maybe AS2, not that. Basically, let me give you an example. So my name is what? A small example. I'll just use my my title, OB Nexus, my persona name, my avatar name. So that can be for my company, everything. Because I don't change it. This is a schema I can't change for my avatar name. So you got an avatar name, what you want to identify as, nothing your face no more. Because I'm black and I want black. I know I'm not black. I'm not. So basically, the coding system was like this: 0, 2, 1, 2, 3, 4, 5, 6, 7. 0 to 7, and then you get 0 to 7, and then you get 1, sorry, 0 to -7 in two ways. So basically, if I start reading from the left, I get what? Start from 0 index, and then go to 7. If I start reading from the right, I get what? Right index. So how this works in the framework is this: I get a reader codon and a writer codon. They do the same thing. So I can read and write in segments. And how this works is this. So go back there. Let me just see what I can get my docs. I don't really have a doc I can write for this. I mean, I can load up a new system, a new terminal, and run that file, but I don't really want to. Basically, this is what I'm saying. So you got you got like admin time and standard. This is just the problem here. So this is this long. So basically, it's got a system and a half. It's like a it's just basically cutting the problem in half. Basically, it's like it's imperfect. So this is the genome. This just means AS. This is like the structure squared. AS splices. It's not the other one. It's not the gene one. It's not the. It's how basically it's splicing, not slicing. It's splices. It splices does not slice. It's like it's not slicing. So slicing gets a whole segment of code instructions to act on it. And Mmuko coding or decodons. But it doesn't. This is splicing, so it works on the substrate or smallest substrate. So it works on half the code. And what is important because it can do it in real time. Smallest coding. So for example, adenine. I'm gonna go to the coding right now. So this the code this is just because my name is Nani. So if I want to read 3 letters from my name, read. It's like it's Huffman encoding. Let's see what I have here. Yes, so this is the Huffman. Yes, this is the Python implementation. So this is the AVR rotation. This is the Python implementation. This is like your gene code. So it's like basically adding time and basically this is something called class lossless. It's a lossless encoding system, so it doesn't lose any information. Lossless splicing system. It's like it's lossless because it doesn't have to store information. It doesn't have to lose any information. It's just using no energy to do it. It just does the job without extra complexities of executing it. So it's basically when you read a code and you write a code and you can execute it, but the execution has energy. So when you have energy to execute something, you have to have the energy go back to the system, and that can degrade more stuff. And that's why I don't like slicing. Slicing is banned from my business as a policy. So use this one, guys. So if I read from the second index, so the the first index, and then to the fourth index, to the one to the 5, 1, 2, 3, 4, 5, to the fifth index. I have the other one will be from the first index, which is U, to the fifth index. 1, 2, 3, 4, 5 B. So you get 2 codons. This is the power series equation. You get like a 2b. 2 is equal to b. So the index of 2, b is equal to 2, and then that's the 2. X is equal to 5. And b is equal to 5, and then you get u is equal to 2, and 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I is equal to 5. Bidashes. So this one is just the range to start and stop. So you get 2 ranges. You can start here and stop here. But this works on the substrate. So it only works on series, not sequence. It only has sequences of instructions, not series. So it doesn't work on heterogeneous data. She's just encoding. So this works in series. You can work on one type of information, not 2 types. You can work on adding and timing sequences, adding timing, nodes, but it doesn't have. There's no cytosine guanine. You can't work on adding timing and then get the cytosine guanine sequence or a guanine in that series. You can't. It doesn't expect any guanine because guanine means that adding timing and guanine doesn't bind together. So that's the first one I'll take. So that's AS2 Pliden of a Mmuko system. So basically genetic topology mesh. Next up, so what that means is like if I read, if I start from 1, I get a B to B to a B I N E, and I stop at 5. That's 5. That'll be B next. Bind. So I get bind for my first output. Output is bind. But then bind. Then we get from my so get my second one. This my start. It's gonna be my start code, and I want to slice my start one I want to slice out first. Chop out from the RNA sequence. Two, because you can chop out and replace it. Read and write. You can get the other one because it's just easier method. You have to read it twice, basically. And you get one U X E N U X 1 2 1 2 3 4 Unix no 1 1 2 3 4. So you get 1 2 3 4. So you get UXEN. That's a bind. So if I want to use this, I can get and do bind UX. Basically, I just try to put them together, and I can use like a vector. So the first one is start and stop, and and I can use it to create new genes because this is example of my name, but this is not really a good example because it's not related. Now, what am I doing? Okay. So let me join. Basically, the other one I'm gonna do. So we got a code on. So now let's start doing this properly. So how this works now in practice for the computers is somebody got a codon. Now a codon what does reading? It's an RNA sequence. So you can read RNA sequences and series only. So because you can read DNA, but it takes time, so you don't use a codon. So I'm gonna give it the real raw thing. So I'm gonna give it a permission. So you got RWX. So basically, I'm trying to do this in real time sparse data because if something is dynamic, you don't wanna a model is dynamic. You don't wanna have it wait for you to act. You have to be acting on the fly. You have to be actively doing the job. And this is called hot swapping. Hot swapping. So hot swapping is like a hot swapping resolution. If the artifact is dynamic, it doesn't wait for anyone to give instruction. It just does it. So because it does the job on the fly. It doesn't have to wait for someone you to get involved with the consensus. Because you already gave you consensus to action that system with that synced tri-directed sync topology resolution. So we got like a system here. You got a codon. A codon is what? A codon what takes the parameters in area. It's an area. It's like a little line. So a parameter is like a code that can read line. Let me just give you an analogy there. I don't want to give you another analogy. Sorry, Nabi. So this one. Yes. So basically, a codon is a little geometrical magic thing. So I'm saying to you guys. So what did I keep it? So let's keep it here. No, this is it. No, don't miss it, man. So I have to try to do properly. Okay, I'm not so basically. I don't know, guys. Hold on. Let me just do it myself because I just can't find it now. I think I kept it somewhere else. Oh, so I'm gonna give you. So the codon is what? Because I already got it again. So the codon does. So you got a codon. A codon codes. What is it called? And you got a decodon. Decodon. So you got you get like a codon and a codon, and you get what? An anti-codon, namely, and an anti-decodon. So it's like a codex system. So basically, a codon what? Codes first. It codes first. That's the only thing it does. It codes first, and you got a decoder. It decodes first. So it's basically gene modeling. So what a codon does. So basically, the codon works on parameter. That's the parameter. The parameters, they're strings, like they're about topology. They're about topology, but about the length or the width or the height of a DNA strand or sequence or whatever the DNA is doing. So that's you get DNA representation from RNA. So they give you get from RNA, you get reader writer codons from DNA and antigens. But your anticodons are what? DNA and area band. They're area, they work in area. So anticoder have area, they have surface area. Width, length, and height, but they work on surface area only. Just to make sure it's clear, you go coder, decoder, codon. These are two systems that work together. So, back on code repository. So this is gonna be there. So the coder, what? So basically, how does it work? So if I want to code something first, I need to code something. I want to write to it. What is that? what permission do I need? I need a W. So I need one W to write to a codon. Because I actually only want to write once. The maximum time I want to write is once. Why? So I can do other operations. Do other things. I want to do once, only once. Now, if I want to decode on, I want to read and write. Why? Because I want to decode information and read it. So I have to read first and write next. So read write permissions. But if the coder basically I can then do an X. If I write something, I can write it and then execute it. WX. Let me put a box. We can read, write, execute. Execute. Just get this pretty started. But the execute is just iota. So if I'm writing to it, I want it to run. So I put it there for like this like an end. If I want to make a mistake, it's like an inverse codec system. So basically, once you start running it, you can't stop it. Because that means everything will break goes on the fly. So this way it matters power. So you get anticodon. What's an anticodon? Now anticodon is an area. So if I have a codon, I have an anticodon. That means the right squared. So right times right. Right plus right is what equals right squared. So that's just one anticodon, like a length. But the right squared is right plus right is two right. Now two right squared is what? Length times width, and that's width times length. Length times width, which is the 2 right squared, is 4. Sorry, 4 right cubed, because 4 like 4. You need 4 writer 5 to code 4 writers to have a codon. That can execute, can just run it and fix the problem. Because the execute just means it works. If it doesn't work, it breaks. So you have to do nothing for that. And you get an anticodon. What the anticodons do? Antidecodon. So the anticodons has the same thing, anticodons, but because they read and write. But so you get so when you read and write, we have a reader and writer. You get this reader and writer. Read and write. Read and write. So RW. R times RW squared is RW that RW equals 2R 2W. So 2 read and 2 writes allowed minimal to do some kind of genetic operations. Because I'm using my concepts of genomics, it's a computer, so I want to do the computer. And you get 2R squared. No, you get the 2R times 2R, which will give you 4R squared. 4 squared times plus 4 squared and 4R squared and 4R 4 writer squared. So you get because you don't use 4 4 because R times R is so you get you get 4R. So you get 4R and 4 dot right. So you get maximum and minimum, and you get the execute. You can just run on the fly, because if that's not executing, there's something wrong. Because there's some computing there. So there you go, the coding system. Now you get the other one. So this works in areas. So you need to cover the service area. So I'm saying, so you now got the same thing. Which they are some kind of like model. So this is the what's this? This is the 8 thing. This is the other thing. Let me show you what it is. So this is the example. So this is what it looks like in practice. So let me give you what it looks like in practice. So this boy, it's just a diagram. This is a truth table, but it's like a suitable for genetic modeling, but for sparse genetic ones. You get like the 4 states of it, but they do it in one go. So if I want to do it in 2 sets, it'll be like a 2 goes, because the quantum computer doing it, because this is a sparse model of it. And how this works? So for adenine thymine, very important, guys. Adenine thymine, AA. Right, so you get so AA and TT. TT equals AT and A. So this is called adenine genetic code. So this is genetic code. So this is the code, but this is now the upper level. So this is just basically let me give you the other one. So this is just like this one's are called all these are called enzymes. These are like your saliva, things that break down food for you when you chew. These are like the smallest stuff. These are the smallest, the easiest things. These are why, because they work on the smallest things, but they do the job. They are called enzymes. So like it's pets, they break down or the balance of your hydrochloric acid in your stomach, whatever boogers you have in your ears. They do their job and they leave you alone. Your nose booger, your ear booger, all of that nonsense. Okay. Now we got the actual one. So you get AA. Now AA2 basically get the same one, AA, small a and small a. Small a and small a, add the mine, and a small a and small t. So basically, see this same thing. This is the same thing. This is the codon system, but this is the full form of it. Adenine, thymine, and cytosine, guanine. For now, guanine. So basically, you got us two small a's and two because you know this is a model area, the surface area. So, for example, if a one a is what? If you're one, you can read one a, but one a does what? Okay, let me just get it. Let's jump properly. Oh, 40 minutes. Uh, 40 minutes to get 1a, 2a, 2a equals to. So you get like a 2t. It can be like this. So this is the model here. This is sparse. Why is it sparse? This is this is like a V. With a so this is like a two. This it comes in here. This one comes in here. But these two connect. This is one. This can be one sequence. One representation of it, or one topology with representation of how it looks, or it can be this. This can be the same thing. See this one? The same thing, but this is the parameter, just lines. I'm using it to represent it. For the system of the so we get A T A T A T then A and then AT and then adding timeline. So yes, so basically this integrated. So my tweet is so basically you get adding then timeline and then tiny nucleotides. These are called nucleotides. But you know, you got like a nucleotide, you got anti-nucleotides. So basically, it's all genetic modeling. So I'm just giving myself a lecture of it. So we don't want to myself to win, basically. So you see this model? You see this like here, you get T then A, T A, T comma A. That timeline is bound to added in that order sequence or series. And then you get adding bind to time in that sequence. So they can be sequence. These are the same thing. But it just depends what you need. Now this nucleotide, the same thing. So this is what this is T then A. This line, then either T, just one A first, and then write T next, you know, and then and then you get to this line, which is what they connect into the other side for cytosine and guanine. Hopefully that's how it works. But you know, basically the nucleotides can bind to the where this like topology mesh here, which is my claim. I hope I'm right. But you know, whatever they agree on, based on whatever is gonna evolve in the best smallest units is best. But you know, this is basically this side is RNA red, and you know this RNA has a what? Oh, it's like an adult to me. Same thing. So the RNA is like a line. See, it's like a 45 degrees line because it's just bound to the DNA strand. Basically that's the DNA strand there, in the middle. This is strand. Let me try this strand for myself because I'm like strand. This strand allows you to bind. But it's like a weaving thing, so it's just unwind. Or this what gets unwound, the strand. Let me just make it like this is strand, so it gets unwound. But it's just a model of it. So either can bind the timer, something going that way with the strand. But you know the strand has to wind this thing there. It's called strand. And then the codons. So we get nucleotides, get anti-nucleotides. So these anti-nucleotides are just the adenine thymine genes. But whether they're in series or sequence. So the nucleotides contain the genetic instructions of what. So you get like G then C, then A then T. Best be read on one first to go from DNA to RNA. You know, because because it's like compressed. It doesn't. It keeps it like lossily compressed. It doesn't cause to break the system. Oh, for 7 minutes. Okay. Same thing for this one. Let's move on now. Computation. Basically, you have to do this now before it gets 15 minutes is fine. Let me, I guess, any time. So, this is the gene layer. So let me just do some computation on it. Because I'm trying to remember my biology now. Okay, yes. So you see the curve, the arcs, the two axes are the same thing. Because it just rotates, because it just gets it up, dropped out. Let me show you the anticodons. Now, the anticodon is this. So if you have this codon, this one and this one, you have the other mesh one. So you get this one. And sorry, and this one, sorry, and sorry, and this one. Oh no, stop, shut up, shut up, shut up, shut up, shut up, shut up. Oh, I'm not even recording this, man. Oh, anyway, so basically, you get this one. And so, see this one? See this? This perimeter has this area surface. So this one can hook to this one. So for just the antibodies, so they work together or work against each other because that's how virus work. So this one rigid one can reach this one, but no, this curved one can reach this one, big one that says surface area to it. So this curve basically can hook together. But, the antibodies, the anti ones are like the same thing. So you got the anti DNA, the anti A, but it covers the area of that surface. That's like the whole mesh of the anti time and duality. It's isomorphic to the system problem. What now? Okay, for 5 minutes, I can stop now before it hits. Because I'm already over to open the video. But let's just take the time to stop from here. So that's my introduction to it, guys. Basically, if I don't post it, I'll never always and it's not for you guys, it's for me, because I'm meant to do it myself for my PhD, because I'm in my room and because I'm giving house and I'm sad. I'm not sad about it. I'm going to Nigeria anyway. Let me just finish now. So if I go to so basically the area is computed to same process 2A's 2A. I can get 2A. I can get A and 1T, and then get 1T and 1A, and then get 1A and 1T. But that's 1A, AT, timeline first, AOT to bind it. So how you compute it is like A times A equals A. Now you get T times T equals T, equals big T. So a small T, big T is then you get so basically you can multiply it as so the perimeter will be A times A. Whatever the surface area of the codon for the A was, and A times A equals big A. That's the A squared. But this will be the perimeter, the areas to go into the gene based on the strand model, and then you get the opposite one, the outside, the X Y layer, the dimension Y. Y and Z and the structure of the surface. So this is surface structure model based on the how it's meant to curve, how it's meant to unwind. Let me go stop the video now. Thank you guys. Let me go now. Oh.